Good morning, buenos días. Desde Casa de la India in España. Good morning from Casa de la India in Spain. We are hosting this session, which is an international session today, a webinar on the application of Raman Spectroscopy to space and science, which will be integrating presentations by Professor Fernando Rull from the University of Valladolid, ERICA Research Group, as well as Dr. Guillermo López-Reyes and Dr. José Antonio Manrique. It's a pleasure for me to be hosting this session, which we're doing in collaboration with the Embassy of India in Spain. And we also welcome Ambassador Sanjay Verma to have been so kind and sparing time with us and spending a bit of brainstorming here on science and technology cooperation. And of course, to our Indian partners, which have been very great, very also collaborative in disseminating the session, which will be live on YouTube as well as through Zoom, and in particular ISRO, Indian Space Research Organization, which is the prime research organization in India, and of course Indian Institute of Space Science and Technology, also from Trivandrum. So we are very grateful to this collaboration, and we also greet the embassy in Paris, which has been a link, Indian embassy officials who handle science over there. So without further ado, I'll pass the floor to Sanjay Verma, and we will then introduce the panelists.
Well, thank you, Guillermo. Warm greetings from the Indian Embassy in Madrid. May I begin by acknowledging the presence and participation of Professor Fernando Rull, Dr. Guillermo López-Reyes, Dr. José Antonio Manrique of Valladolid University, scientist Mohammed Hassan from ISRO, Professor Umesh Khadane from Kerala, the Indian Institute of Science and Technology, Space and Technology, and my colleague at our embassy in Paris, Tushar Fadnis. A very warm welcome to you on this platform, a platform which today marks and celebrates the work of C.V. Raman, one of India's greatest sons, and also on the occasion in a series of programs to mark 75 years of Indian independence. This is all about science, but I am a diplomat, so I shan't speak so much about the science aspect. C.V. Raman's contribution to space science is a given, and we are only discovering what he set forth many decades ago, which sort of put in place the mapping or the fingerprinting of space for future research and developments to take place. We celebrate every 20th February as a C.V. Raman Science Day in India, as a tribute to one of our finest scientists. As a diplomat, the space has very different connotations for me, for my colleagues, and for countries too, because space is increasingly becoming the new arena of contestation, cybersecurity, oceans, etc. But space is going to be an area of contestation, even while it is being discovered. So these are two parallel tracks at the same time, while you, my dear colleagues and wonderful scientists and minds are putting yourself and applying yourself to unraveling the mysteries of space. We diplomats look at it slightly differently, while at the same time also acknowledging the commercialization of space, on how travel to space is now becoming increasing possibilities, becoming more affordable. We have been told that we are on the cusp of using or tapping solar energy from space to our planet. Also, communications are being put into place even while we are years away from physically locating ourselves in space for long periods of time. The communication technology is available for us to use it whenever we start populating space. As a species, we are on the threshold of becoming multi-planetary, as it would appear. But again, all this wouldn't have been possible without the wonderful work all of you do. May I congratulate Professor Fernando Rull for the fantastic success and work with the Perseverance mission with NASA. I think congratulations are due here, and so please accept felicitations on this wonderful work, and which you so kindly also acknowledge and give credit to C.V. Raman somewhere for making this possible. India has worked closely with several countries in the space arena, with France for sure, with NASA, with the Russians, and I can see that with Spain too, we will find a new partnership. As we do in several other areas of bilateral cooperation, science and space particularly, and today could be a beginning, I'm sure. As the proceedings move on, we will find synergies and common areas where we can hold hands together. Let me conclude by wishing all of you a very productive seminar, and I thank you for your time in making this possible. Over to you, Guillermo. Thank you.
Thank you so much, Ambassador, for your kind words. Indeed, this is a wonderful opportunity to strengthen Indo-Spanish relations in the science and academic field. We want to say also a warm welcome to Paloma Castro, the Pro-Vice Chancellor of International Relations, University of Valladolid. I'll pass the floor to her to give us her impressions on this initiative. I must, of course, say also that University of Valladolid is not only one of the oldest academic institutions in the world, which is almost 800 years old, but the university is also supporting India relations for many years, and they are board members of Casa de India, along with the university, along with the Embassy of India and the City Council. Paloma, please, thanks for joining us.
Thank you, Guillermo. Just a few words to say that for the University of Valladolid, this initiative, this webinar, it is for us, it is very important because it reflects the strong collaboration between the Embassy of India and Casa de la India. So just wanted to highlight this point and wishing all the best for this webinar. For us, we are very proud of this team led by Fernando Rull. So I'm sure it will be a success. Thank you so much.
Thank you, Paloma. We now greet our Indian partners from ISRO, Indian Space Research Organizations, and IIST, Indian Institute of Space Science and Technology. I would please request Professor Umesh and also Dr. Hassan to introduce their institutions briefly.
Maybe we can start with Dr. Das.
Yes, please. Sure.
Yeah. Good morning. This is Dr. T.P. Das from the Indian Space Research Organization, and I have with me my colleague, Mr. Hassan. Good morning, Your Excellency, Ambassador of India to Spain, Dr. Guillermo, Professor Fernando, Dr. Paloma, dignitaries and the scientific community. I take this opportunity to thank the organizers for this wonderful webinar, for organizing this event of high scientific relevance as a part of celebrating 75th anniversary of Indian independence. And it is our pleasure to be a part of this and say a few words on relevance of this topic for Indian space program. On this occasion, the selection of the topic on Raman spectroscopy is symbolic. Raman spectroscopy represents a fundamental work in physics that originated in the colonial era of India. Out of introspection of a young Indian who is today celebrated as Dr. C.V. Raman, Sir C.V. Raman, on the blueness of the sea. The Raman effect is one of the most celebrated ones today, and it is an apt example of what we call today the translational technology. What started as an investigation on the scattering of light and its energy shift by the vibrations of molecules of matter found its numerous applications in planetary science, forensics, pharmaceutical industries, non-destructive testing, and many other fields. Now we, coming back to the Department of Space, Indian Space Research Organization, are engaged in scientific missions which necessitate ground activities like non-destructive testing, chemical analysis of samples, to name a few, where Raman spectroscopy plays a significant role. We identify and characterize the rock-forming mineral using scanning electron microscope integrated with micro-Raman spectrometer. This is a technique which tells us about the chemical composition of the meteorites which make it happen to reach the surface of the Earth from space. Raman effect is also a potential tool for the lander or rover-based exploration of planetary surfaces. The characteristic of Raman shifts enable us acquiring structural information of the chemical fingerprint of any rock-forming material. So in this context, I express our happiness over selecting the most appropriate and knowledgeable speaker on the team in the field of Raman spectroscopy and exploration. We look forward to listen to you. And on behalf of the scientific community of ISRO, Department of Space, India, I take this opportunity to thank the Embassy of India, Madrid, the esteemed speaker and the members of the organizing committee to have arranged such a scientifically stimulating event. Thank you all.
Thank you so much. It's really an honor to have ISRO on this panel. It's amazing. I can't believe it because I'm a big fan of ISRO. So I used to pass by ISRO when I was a student at Kerala University in Trivandrum. So congratulations for your work. Now we proceed to Professor Umesh. Please let us know more about your institution.
Namaste and buenos dias to all. His Excellency Sri Sanjay Verma ji, Ambassador of India to Spain, Pro Vice Chancellor of University of Valladolid, distinguished members of Casa de la India, Professor Rull and his colleagues, my ISRO DOS colleagues, and all the participants. It's a great pleasure to interact with this distinguished team here today. It's an opportunity for IIST, as perhaps you know already, that IIST is a very young institute, so we get a very nice opportunity to interact with very senior people here. And I must thank Professor Rull and his team and Casa de la India to arrange this, of course, in collaboration with the ISRO liaison office in Paris, as well as the Embassy of India in Madrid. So IIST, Indian Institute of Space Science and Technology, it's a very young organization. It's just 14 years old university. It's Asia's first space university. This was created under the aegis of Department of Space, Government of India. So obviously we have a very strong bond with the Indian space program and we benefit a lot from that. We have a few undergraduate programs which basically cater to the ISRO's requirement of engineers and scientists. Then we have 15 master's program and a very strong PhD program with more than 200 PhDs. We are very proud to say that more than 1,000 IIST alumni are members or employees of Indian Space Research Organization, and 70 more are going to join this year in a few months' time. But apart from just the academics, we continue to do our research, and we have 7 departments and having about 100 faculty members in various areas of expertise. Our institute is not really very big. We have 7 departments and 100 faculty members, but still we are counted as among the top 35 technological institutions in the country, and we take pride in our collaboration with the space technology and space science. So our programs are very largely driven by space science and technology, though we have very broad-based expertise. So in various areas, we have experts in thermal, propulsion, aerospace design, control systems, robotics, power systems. Our physics department, we have a strong expertise in optics. Our astronomy group is perhaps the largest and the strongest astronomy group in a university environment in the country. And we have a very strong atmospheric and remote sensing and other space application areas in our institute. We are also part of several international MOUs. Our toppers from the undergraduate program engineering undergraduate programs. They join for the Master's or Master of Science program in Caltech. And amongst the 8 occasions in last 8 years, half the time our students stood first in their respective MS programs in Caltech. We have similar internship program MOUs with Caltech, JPL, and Australian National University. We have several research related and academics related MOUs with Technion, Narita, and also ISA Supero, and so on, just to name a few. We are investing also in a lot of space research and developmental activity. So for that, we have established a small satellite and payload center. It is called SPACE in IIST, and all the interdisciplinary research feeds into various projects there. We are part of ISRO's interplanetary mission. We have our own student satellite program. In fact, one student satellite is supposed to be launched very soon in a few months, which was built in collaboration with LASP. And we are hoping to get our own home-built satellite also very soon in space. And we have proposed a very advanced space telescope for exploration of exoplanets, and that is in advanced stages of consideration. And we are also preparing a similar advanced level mission for possible exploration of origin of life and organic material in our solar system. So in that context, I think today's seminar by Professor Rull and his colleagues is something which is of very important and very valuable to us. So I once again thank all the organizers for bringing us this opportunity. And on behalf of IIST, I thank you all. Dhanyavad, namaste, gracias.
Thank you so much, Professor Umesh Kadane. I'm sure we will add a new MOU soon to your range of collaborations by integrating also projects with the University of Valladolid and the team headed by Professor Rull. We now proceed to the presentation of the speakers. The team that University of Valladolid and entire Spain is very proud of because of their recent and long-standing successes, headed by Professor Fernando Rull. I'll very briefly introduce their background and curriculum. It's very large, so I'll sum up the main highlights. Starting with Professor Fernando Rull Perez. He has a PhD in physics from 1976, for which he was awarded with the Distinguished Doctorate Award. Since 1989, he's the chair professor of crystallography and mineralogy at the University of Valladolid. Most of his scientific training was done at the universities of Montpellier, Bradford, and Copenhagen. So in all these different countries where he has done his training. And of course, he has had research stays across Europe, universities such as Nancy, Sofia, in Paris, London, Barcelona, and Madrid. Since the year 2000, he's a senior researcher at the Astrobiology Center, research center belonging to the Spanish National Research Council, and which is associated to the NASA Astrobiology Institute. Currently, Fernando Rull is the PI of RLS instruments of Exomars mission and the co-PI in SuperCam instrument of Mars 2020 mission. Thank you very much, Professor Rull, for accepting to be part of this seminar. Next, his colleague, Dr. Guillermo López-Reyes. He has a PhD in physics focusing on automation in data analysis of the RLS instruments with insights to other spectroscopic techniques. Also belonging to the Associated Research Unit of University of Valladolid and the National Center CSIC of Spain, National Center for Astrobiology. His major areas of activities and research are the development of science prototypes for Exomars RLS instruments and development of algorithms for signal processing and automatic acquisition of Raman spectra. Currently, Dr. Guillermo Lopez is working as a science research specialist in the ESA, Exomars, and NASA Mars 2020 missions to Mars. He's skilled in spectroscopy, research and development, engineering, and project management in space projects, algorithm development, and data analysis. And the third speaker will be José Manrique, who has a PhD also in physics from the University of Valladolid. He was selected to participate in several internship programs of Castilian regional government and IT, a company based in Salamanca, where he has been working, and since 2012 has been awarded the Argo grant by Spanish Education Ministry, participating in international projects. Between January and October 2012, he has been working as the Technology Transfer Officer in CIMNE USA, the US branch of CIMNE, the International Center for Numerical Methods in Engineering. Wonderful, impressive background of these three speakers today. So we won't take more time of your presentation. So please, Fernando, you may start, and we are all ears and senses to your presentation.
Okay. Okay.
We'll certainly have time for Q&A at the end. Thank you.
Okay. Okay. First of all, many thanks to the University of Valladolid, the presence of our Vice Chancellor, Paloma Castro, is very, very welcome. Also to Casa de la India and Guillermo Rodriguez. Without the support and the work in between the University of Valladolid and Casa de la India, this webinar was not possible. Also, many thanks for the presence here of many important personalities and many important scientists, starting with the presence of the ambassador of India in Madrid. Many thanks to be here also in the webinar. And our colleague in Bangalore and ISRO. Many thanks also for your participation. I hope that this webinar will be the starting point for fruitful collaboration and other common activities. I will start with, now I need to share the screen. It's okay. With some very brief historical comment about the Raman discovery and the implication that this discovery had, not only in the particular application of the spectroscopy, but also in the science in general, and in many of the applications on science, industry, and at the end in space. You know, all you know, of course, that 28th of February is the National Science Day in India. This is because Raman, C.V. Raman, published in the newspaper this short text describing the discovery. And the curious thing in this description was that he called new theory of radiation. Curious, because in fact there was not exactly this, the physics behind the discovery was not exactly a new theory of radiation, but he was pioneer in presenting the result in newspaper before to publish in scientific journal. The second point is here from the historical point of view is the letter that the President of India addressed to the nation on 2005, that was the centenary of the Albert Einstein miracle year. This letter also reflects the importance of the Raman discovery in the history of the science and the history of India. Of course, Raman immediately published in a scientific journal, in this case, the very prestigious Nature journal, the discovery. But now he called a new type of secondary radiation. This was more appropriate with the physics behind the discovery. Here you can see this only for the public in general, some picture and some detail about the biography of Raman. Maybe at the here with an interesting comment, because one of the last recognition for Raman was the Raman. So I don't know if you are seeing the screen. My screen. You are seeing my screen totally?
Yeah, we can see.
Yes.
Okay, because I have a little problem here in my screen. Okay, now only to comment that he was obtaining recognition along many years, and this is one of the last when the Raman effect was designated National Historical Chemical Landmark. But the Raman effect was really only the Raman effect, or it was also a coordinate discovery. It's necessary to remember that at the same time in Russia, Mandelstam and Lazar discovered the similar effect few days before Raman published the first news in the newspaper. But unfortunately, they don't publish immediately this result, and they had some problem, not only because this, but in particular Mandelstam, because he was not in a total agreement with the Soviet system. But also important in France, other research people, in particular in Paris, discovered the same effect. It was called Caban-Duré effect, and it was discovered by Alfred Kastler, Pierre Duré, and Jean. Sorry, with my screen.
Yes, we can see it. We can see it.
No, this is just in my screen. Okay, they discovered the same effect. The important thing for the history of the science is that very few discoveries of this impact were simultaneously discovered practically at the same time. This is a very rare in the history of the science. And for us, another important aspect is that Jean Caban moved from Paris to Montpellier, and he started to developing Raman spectroscopy in Montpellier. And when he died, another professor, Professor Lafont, continued the work in spectroscopy, and the University de Valladolid take contact with the University of Montpellier at the Raman spectroscopy laboratory at that time, at the time of Professor Lafont. And then the history of the Raman became from Paris to Montpellier, and to Montpellier to Valladolid. I don't like to enter in detail for the physical description of the Raman effect. But it's necessary to mention that this is a part of the general process of interaction radiation matter. In particular, we have two main processes in this interaction process. That one is the absorption, that is the observation of any radiation that is traversing a material. And the second aspect is the scattered radiation, that is all the other radiation that is emitted in another direction different from the incoming direction. And in particular, in this case, if we illuminate the material with a monochromatic light, in particular a laser, we observe in the scattering light, we observe a combination of emitting light with different wavelength, or with different wavelength, with number, or with different frequency, that reflect an important part of the structure of the matter. The main component is emitted with the same color or the same frequency or the same wavelength that the incoming light, but other are emitted at different wavelengths with different waves number, and this is the Raman radiation. This is the secondary radiation, and this is the effect that Raman discovered for the first time. The problem, one of the problems that this secondary emission has is that its intensity is very, very weak. It's many order of magnitude weaker than the incoming radiation, for example, the laser. And in this case, or in many cases, near 1 billion less than the incoming laser. That induce this difficulty, produce in the history a lack in the utilization, in the application of Raman spectroscopy in a wide sense, and remains mostly inside the laboratory for fundamental study in crystal, gases, liquid, and so on. Until the technological advance overcome this main limitation, that was the 90 scattering geometry. In the right part, you can see the original 90 degrees geometry used by Raman. In this case, of course, not with a laser. At the time, there no laser at all, but using the sun light. Then, when it was possible to perform Raman spectroscopy in the 180 degrees Raman configuration, the situation changed dramatically. This is the general configuration for a instrument, a Raman instrument with this configuration. We have three main units. This is the illumination unit. This is the Raman probe head that illuminate the sample and also collect the scattered light. Here, there is the main secret or the main technological achievement in this configuration, that is how to reject this very intense light that is emitted with the same wave length or with the same wave number, and how to suppress this and how to allow that only the Raman signal enter in the spectrometer. And the third unit is the spectrometer. Of course, with a detector, data transmission, and data interpretation. The main characteristic of the Raman analysis can be summarized like that. In this configuration, no physical contact with the sample. No sample preparation is needed. Analysis at micro and macro scale are possible. And also is possible the remote analysis and very fast observation, in particular with the CCD detector. And with the interpretation is from the vibrational mode, is possible the molecular identification and the structural characterization of the material. That means the structure and the chemical composition of the material analyzed. This is why this technique finally led to the idea for the different space agencies that Raman spectroscopy could be a powerful technique for planetary exploration, and in particular for analysis on Mars. And the first experiment and the first development for such purpose start in 1995, 1996, about that, and arrive in 1998 to the first instrument developed for Mars exploration. This is an instrument developed by Larry Askin and Alien One in the States, and was proposed for MER, for Spirit and Opportunity. Finally, it was not considered for the payload, for the mission, and it remained in the laboratory for many years. The second opportunity to include a Raman spectrometer on board a mission was with Exomars, the first mission that ESA proposed in the White program Aurora. And this was the Ex Libris project led by Sylvestre Maurice and I, and it was a combined Raman LIPS instrument. This is important because Raman with other complementary technique as LIPS is, this combination is more powerful than only one of the two techniques. Here, some detail about the Ex Libris project. We propose to perform chemistry, mineralogy, and organics on Mars, analyzing a distance with a pulse laser and with the combination of Raman LIPS, the material at the Mars surface. This is important to note because if you know the history of the Mars exploration with rover in the last year, that part of these ideas were retained for MSL, Mars Science Laboratory with LIPS. Recently, the combination of both techniques was included in Perseverance for Mars 2020 mission. Maybe extra curiosity. Not only is necessary to consider the potential of the technique, it's necessary also to perform the development and only to have an idea where what we are talking about is to consider our former instrument at the University of Valladolid, the Raman spectrometer in the 90 degrees configuration with weight approximately of 250 kilo, and the Raman we developed for Exomars, that was the first Raman spectrometer full qualified for space, that weighed 840 grams. Another interesting aspect was the configuration of the spectrometer. In this case, we were working very hard on the transmission spectrometer concept. Not only because this is a configuration quite luminous and allow the collection of many photons, but also, in this case, we were considering that the geometrical configuration of the Raman spectrometer for Mars follow the same configuration than the first Raman spectrograph that Raman used for the Raman effect discovery. This is a very brief description of the different prototype, the different model that we developed with the team, leading to the final spectrometer that is now inside the Exomars rover. But we not only need to develop the instrument, we also need to develop the associated science. Here is a brief summary of the associated science that we are developing. And in particular, I would like to stress the science that we are developing using prototype that derive from the model we are developing for Mars exploration, and with many places in the world that we use for analysis in situ. It is necessary to understand that no place on Mars is similar to the place on Earth because are two different planets. But the different geological processes and the mineralogical processes are very similar. And then studying these processes is possible to perform model for the science to be developed on Mars. And in the right part, you can see one example of a more sophisticated analysis of this potential terrestrial analog. Is the participation in the ExoFit project. That was an ESA Airbus project in which we analyzed material using the rover. This is an engineering model of the Exomars Rover. In Tabernas, we selected the site, and this is the rover operating on the drill. Guillermo will explain in detail all the aspects related with this rover and the instrument inside, and also in Atacama, Chile. This is only a curiosity. This is our laboratory and our collaborator of people working on site. With this science, also with the science that we perform in the laboratory on meteorite and other material, we are prepared for research on Mars and also for interpret any, in principle, any data that our instrument can supply and send to Earth. I would like also to emphasize some other application that derive from the in situ analysis using this prototype. And I consider here in the presentation for the environmental problem, this acidic water product of the mining activity. Rio Tinto is a very good example, but there is several other examples in Europe, across the world, in which with the Raman spectroscopy in situ, we arrive to detect and quantify the different chemical species in the acidic water. And from this Raman data, it was possible to perform thermodynamical model about the composition and also about the precipitation processes. This process has an important impact. Also in Burgos Cathedral has an important problem, this very important degradation problem, because some salt and precipitation at the surface as product of the solubility of internal salt in the phreatic layer below the cathedral, and this is a very, very serious problem. Raman spectroscopy was able for detecting salt in the surface, and from this detection and interpretation was possible to perform model about the precipitation process and the sampling, also possible solution for this tremendous problem. Another important thing is to analyze caves. Caves are important not only for Mars, because mineral produce and also transform under dark condition, but also because bacterial activity is also is produced on the same dark condition. And there is several implications also related with the conservation of the cave, because many caves are used for tourism, other only for studies, but in principle is necessary to preserve this cultural heritage. Here at the right part, you can see our analysis at the Altamira cave. Altamira cave is a world famous cave. It's a very, very important cave. And we analyze and interpret the pigment on the cave. And finally, I will like to thank you all for your attention, but stressing that at the end, the human team is the key. Without all collaborators, all the people that participate in the laboratory, at the field, interpreting in the interpretation of the data, sampling software, etc., all these achievements are not possible. Many thanks.
Thank you, Professor Rull. It's truly fascinating. And once again, congratulations for all the work you and your team have done. It's amazing to see how a discovery in one corner of the world has had so much impact and so many applications in science, thanks to your efforts and those of your colleagues. I believe now it's the turn of Dr. Guillermo López-Reyes, correct?
That's right.
His paper on the subject. Thank you so much, Dr. Guillermo. We would like to hear your presentation.
Okay, thank you very much. Thank you to all the panelists and everyone that is here today. I'm really thankful for the opportunity to be here. So I won't delay too much, and I'll start sharing my screen. Okay, so I've entitled this part of the presentation, the search for life on Mars, because this is basically what we are doing on the Exomars mission, which is the mission I'm going to talk about basically. So we all here at the group participate in all the missions, but today I'm going to talk only about Exomars. This is a very interesting mission because, the main aim of this mission is to search for life on Mars. But first of all, why Mars? Okay, so Mars, 4,500 million years ago, was wet as the Earth was. So it was very similar to the Earth. And we know it had water, and we know it had a magnetic field, and so we know it was very similar to the Earth in the beginnings. So what happened? What happened that the reason why we have Mars like on the right side now is basically explained by the difference in sizes between the Earth and Mars, because they were both formed at the same time and they both had the same characteristics. But what happened is that Mars being so small or so much smaller, the ratio between the surface and the volume is much higher. So it cools much faster. So if it cools faster, it means that at some point the nucleus will stop being liquid, and then when it solidifies, we lose the magnetic field. Once we lose the magnetic field, we have the solar wind that takes away the atmosphere, it takes away the water, and so the planet dries. This is a very short and fast explanation. It's much more complex than that, but basically this is what happened, and this is why Mars is a very much so it's drier today. It's geologically basically dead compared to what the Earth is having. Also, there's another thing that is very interesting about Mars. It doesn't have tectonic plates on it. So this means that everything that happened on Mars in the past is like still there. On the Earth, we lose the information when because of the tectonic plates. So we don't have a lot of information of we don't have so many rocks and materials on Earth that are 4,500 million years old. There are some selected points, but on Mars different. We have like this fixed picture of what was like when in the past. So if we go to Mars and look for life there or look for organics there, we are looking at the conditions that were in the Earth also all this time ago. So it's very interesting to look for life on Mars or to look for organics on Mars, because we are actually looking at what might have been on Earth. So we are learning about ourselves. This is the reason we want to go there. So the ExoMars mission has this rover, very nice rover, which for the first time will be able to look for materials that are very deep down Earth, like a couple of meters down. I'll show you another slide in the coming minutes. And this is very interesting. This hasn't been done before. So most of the rovers that have been sent to Mars are considered like robotic geologists, with the Exomars mission, we aim at having a robotic biologist. So this is the main difference between the Exomars mission and all the other missions that have been sent to Mars. So as I was mentioning, so we have this very high radiation on Mars. So the UV radiation only affects the first millimeter of the surface, but this will reduce all the organics that were there. So for sure, we won't find organics very close to the surface. If we go some centimeters below that, the UV radiation won't affect, but we have the oxidants, and this will affect down to 1 meter. Then we also have the ionizing radiation, who has a penetration depth which is up down to 1.5 meters. So the Exomars rover, what we'll do, it will look for interesting spots and will decide that this is a good place to drill and grab some samples from below this 1.5 meters. So we can get samples from down to 2 meters depth. So the potentiality, the capability that we have to get potentially well-preserved organics on Mars will be higher, much higher with this rover than it has been with all the rovers that have been on Mars so far. This is our Exomars rover. It's a solar-powered rover. It has this very nice pan-cam here, panoramic cameras with some instruments on it, and it has these 6 wheels. But we can observe it's quite big actually. It's like a small car. It's smaller than the Perseverance rover, but it's still quite heavy. And we see that the wheels are quite small. But the most important thing about this rover that we can see here is the drill. This thing you're looking here is the drill. So it will collect these samples from down to 2 meters depth and put them inside the body of the rover for analysis. And our Raman spectrometer will be placed inside this rover. So the drill is one of the main important things of this rover, but we also have these very small wheels with a very heavy rover, and we have implemented a system that allows the rover to walk. And this is called the walking wheel mechanism, because we know from past experience in Mars that rovers tend to get stuck in the sand dunes. And of course, with the weight of the Exomars rover, it's quite easy to be stuck. But we have implemented this method, and so you see that this is going to save the rover from getting into these sand dunes, because it can actually walk and get out of these problems. And so these are two of the things that differentiate the Exomars rover from other rovers. And then the most important thing, together with the drill, is that we have this very complex analytical laboratory, which is for the first time, so to say, it's not for the first time, but it's the most clean hardware that has been sent to Mars for analysis, together with the caching system on the Mars 2020 that José Antonio will talk about in some minutes. But here we have the instruments working in a very, very clean environment, which we call the ultra clean zone. And you can see that we have this kind of carousel here in which the samples will be placed. Okay, so we have a refillable container that will be used and moved around. So the different instruments in the analytical laboratory, in which the Raman instrument is included, where these instruments will be able to analyze the sample on the same position of the sample, all the 3 instruments that we have on the analytical laboratory. So for the first time, we'll be able to do a true collaborative science between the instruments. It's not individual experiments analyzing different samples, but for the first time, we'll be able to analyze the same sample by the same instruments. So we'll have information from 3 instruments on the same position. You see there are several ovens here. These are ovens for the mass spectrometer, and we have the calibration targets of the instruments and also the refillable container. So the rover, what we'll do, will move around this sample in the refillable container, and when it finds it's interesting, then we can use one of the ovens to get the mass spectrometer analysis, which might better detection limits. So this is the ultra clean zone of the rover. When we integrate it here in the rover, this is the aspect that the analytical laboratory rover has. And I'm showing this because we can see the spectrum, the Raman spectrometer here, right here, the optical heat is down there, and the Raman spectrometer is just here in the corner. So it seems very well. And the ultra clean zone is just below the instrument. Okay, we can see it here. Okay, so I won't stop here more. This is the rover when it was integrated already. As you can see, it's quite big. You can have an idea of how big it is. And this is the surface platform. So the rover will land on Mars on this surface and will go down through these 2 slides here to get on the surface of Mars. It can go down on one side or the other to avoid some problems during the descent. it can choose where to move or where to go. Surface platform. Okay. So once we get on Mars, we have this surface platform down there. It will do its own science. I won't get into details, but there are several instruments working there. And we'll also have the Rosalind Franklin rover with our drill getting samples down to 2 meters depth with our all instruments and our very nice analytical laboratory rover. So CV Raman will be on Mars. This is how we get the CV Raman's technology to Mars. Okay. But what is exactly our instrument? This is the RLS instrument, the Raman laser instrument inside the Exomars mission. It's basically composed by 3 units, 4 if we count the calibration target, which is inside the ultra clean zone. But the instrument works with 3 main instrument units, which are the electronics, which include the laser, which is a green laser continuous wave that will emit light through this optical fiber here and get into the optical head that will focus the light onto the sample with an autofocusing mechanism, because the flat surface that the rover will provide us won't be really flat. So we have to focus at each point. And then the autofocus mechanism will focus by itself on the surface of the sample and will collect the light through this other optical fiber that will get into the spectrometer here. And then the light will be diffracted, as Fernando explained before, and detected by this CCD. So these are the 3 main instruments, the 3 main units. We have the electronics and laser, the optical head, the Raman probe, and then the spectrometer here. And I think here it is. I like this picture very much because we can see on the left the actual Raman spectrograph that was used by Raman, by CV Raman. And we can see that it's basically the same configuration as the actual RLS instrument that will be flying to Mars. So you can see it's very similar. This on the right is the actual flight instrument that will be on Mars. And you can see that the technology is basically the same. This is a transmission spectrometer in which we have to change the analogic acquisition foils here by a CCD, but that's it. Otherwise, we have the very same technology used by Raman going to Mars, which I think it's kind of poetic, and we are very fond of this fact, and we like it very much. Okay, so once we get to Mars, we have an instrument working on Mars. So what do? We don't stop there. We do science. We need to do science. We need to prepare. We want to use the instrument on Mars as good as we can to get all the best science that we can get from the instrument. So what we are doing now here at the Universidad de Valladolid and also in collaboration with INTA in Madrid and with many other institutions is we are preparing for the mission. And we have been doing this for years. We have been analyzing a lot of analogs, Martian analogs on Earth to make sure we understand what we can gather from our instrument on Mars. Because it will be very precious. Time on Mars will be very precious. Data on Mars will be very precious. So we want to make sure that we get the best science, the best possible science from our instrument on Mars. So for this, we have developed here at the University of Valladolid a system that we call the Raman, the RLS Exomars simulator, or RLS sim, which is basically not emulating the instrument itself, but also emulating the carousel of the rover that will place the samples below the instruments. So here we can do tests in a representative environment, operational environment of the Rosalind Franklin rover, in which we can analyze several points on the sample by adjusting the autofocus and all the acquisition parameters automatically, the same way as the RLS instrument will do on Mars. We can also place the samples in a representative temperature and ambient with a vacuum chamber that is placed below the optical head, and so we can really do very detailed analysis that are representative of what we'll get on Mars. Of course, we have also the flight sphere of the instrument, which is placed at INTA, and we can work with that, but it's not as useful as a laboratory instrument like the RLS sim, because with this instrument we can do a lot of heavy-duty tasks that cannot be done with the flight representative instrument. So, for example, we did an analysis here. This is a mapping of the actual RLS calibration target here down on the right, in which we did like 12,000 spectra, 12,000 pixels. So each pixel of this image is one spectrum, and this was done automatically. We have this very nice mapping of the surface of our calibration target that will allow doing a precise combined science between the instruments of the Exomars, thanks to this system we are developing here. Also, this has allowed to develop very many techniques for the analysis. So it's as important to build an instrument and have the best data possible as also having the right tools to analyze it, because we want to make sure that we extract all the information from the instrument and the data that we download. So typically with the Raman instrument, we will detect, we will know what is there. We do qualitative detection of things. And we have shown that with this instrument, in which we analyze at least 20 points up between 20 and 39 points on the surface of the sample, we can get a detection threshold of around 1%. But this is important, this is very nice. But also we have learned using our analytical techniques that we can do quantitative analysis. So based on the multi-point analysis that we do on the surface of the sample, we can do some statistics to know what's the abundance of different mineral phases that we find on the samples, which is very nice because we can do this classification and we can know how much of thing we have there. So we can know, for example, the serpentinization degree of an olivine-rich substrate, for example, or we can know what's the weathering process and what's the scale of the weathering process that has been happening on a determined sample. So this is very nice, and we hope that this instrument, the RLS SIM, will help us during the mission to do this quantification also on samples there. Okay, we have been also using our travels abroad and our travels to Martian analogs on Earth to build databases that will be representative, that are representative of data from Mars. In this sense, we have been working in two different projects. The PTAL is the Planetary Terrestrial Analogs Library, which is a multi-institution project funded by the European Union, in which basically we have these very representative minerals that have been thoroughly analyzed and will be made public really soon to the scientific community with all the data, but also with access to the samples. And we ourselves in the lab, we are building the ADAM, the Analytical Database of Martian Minerals, which is a wider database based basically on or representative of the landing sites of the Mars 2020 and the ExoMars missions. I won't get a little bit too much more in the details. We are also developing our own software for the analysis of data, which is very nice because we can do a lot of things that usually we cannot do, and this will be made public at some point in the future as well. And I will be finishing already, but I want to mention that this is, of course, not an individual effort by the University of Valladolid. Fernando already said this is the human effort, but there is many institutions working here. And hopefully in the future, we'll have to add here the logos of our Indian colleagues, the ISRO and the institutes of our Indian colleagues on this venture that we are starting now. And I will finish now. I'll leave the floor to José Antonio, just to thank again everyone. And if you have questions, of course, we'll be glad to answer at some point. Thank you.
Thank you so much, Dr. Guillermo López-Reyes, and for the whole team to take Raman all the way to Mars. It's truly poetic to see a kind of time machine. If we were to enter a time machine in 1928, and if Raman himself could have entered the time machine and traveled 100 years later and see that the machine he created looks very much like what he had done. And this 850-gram tiny device looks exactly the way he had, created. So I think these things happen in science, and this is also something that gives you food for thought. How time may evolve, but somehow human species will continue creating the same kind of icons and devices, even though we could never imagine. We will now listen to Dr. José Antonio Manrique. Maybe later we come back to that idea of traveling in time. And now the concluding part of the presentation is by Dr. José Antonio Manrique. Please.
Thank you, Guillermo. Thank you to Casa, India, and all the authorities here today with us. It's very exciting for us to just tell you how important is the heritage of C.V. Raman discoveries for our work and space exploration and also astrobiology. I'm going to share my screen now and start the presentation. So I am talking today about the present of a mission that has been working on the surface of Mars since February this year, which is Mars 2020 and the rover Perseverance. It wasn't supposed to happen this way because we had several delays on the European mission in Exomars that Guillermo presented before. But at the end, Mars 2020 ended up being the mission that carried the first Raman spectrometers to space and giving us the first Raman spectra from out of the Earth. And it's quite interesting because we have 2 Raman spectrometers in this mission. And it's a very interesting mission that I would like to summarize here today in this webinar. The mission is a really high heritage mission. It has a high heritage from previous Mars Science Laboratory mission from Curiosity rover. Some of the instruments are evolutions of instruments that we had already on Curiosity, and the rover itself is very similar to Curiosity with some improvements. The objectives, however, of the mission are quite different. While previous missions of NASA had the objective to know more about if there was or not water on Mars, if we had an habitable environment on Mars and in the distant past of the planet, this is the very first mission that NASA is sending to Mars with the astrobiology as part of the main objectives of the mission. The mission itself, it's going to research and investigate the geology of the landing site to evaluate if it was habitable in the past or up to what point in the past of Mars. We are looking also for direct detection of some markers from past life on Mars. I don't want to say present because that would be very, very brave. But we are taking a different approach from the mission that Guillermo introduced before. Instead of taking complex payloads to Mars, trying to look for life, I'm not saying that the payloads we are sending are not complex, but instead of trying to do the direct detection of biomarkers on Mars, we are aiming to take targets, samples from Mars that we are taking back to Earth, where we can analyze them in our laboratories without the limits of the space exploration. And we are also having a mission with very high interest on preparing for human exploration of Mars. And we will have some members of the payload dedicated to this objective. If, as Guillermo said, Mars had water in the past, and we know that, and we have evidences from previous missions of NASA, but the thing is, at some point, Mars started losing the water. And that happened at a very early stage of the evolution of Mars environment, if we compare with the Earth. So we are actually looking for a kind of life that could develop on Mars that is very simple. If we compare with the Earth biological timeline, the first eukaryotic cells happened much later than the start of the Mars climate change, when it started losing its water. So we are not hoping to find really interesting fossils on Mars. We are looking for another kind of evidences, very subtle actually. And for that, we are aiming to catch samples from the surface of Mars where we think those very subtle evidences of life has been conserved and preserved from the harsh Martian environment. Then the rover will put those samples inside these seal tubes that are also extra clean, so we are sure that we have no contamination from Earth. And those tubes will be the first step of a 3-mission plan between NASA and ESA to take those samples back to Earth. The first step is Perseverance using its payload to select the best places to take these samples, prepare the samples, catch the samples, prepare the tubes, and then a second mission, a joint mission by NASA and ESA, will put a small lander on the surface of Mars with a small fetch rover that will take those tubes, put them in a small rocket that will take those tubes to the Martian orbit, where an ESA mission will catch the container with the tubes and take them back to Earth, where the samples will be analyzed. And I'm pretty sure that Raman Spectroscopy will play an important role in the analysis of these targets that we are taking back. We are taking to the Earth from Mars. It's not only, as I said, the research of the aim to find evidences of life on Mars. We are also taking the first steps and helping the human exploration of Mars. In this case, this is a general plan of could be the idea of NASA to go to Mars, starting with the Artemis program that is going back to the moon. But if we look to the right, we see Mars 2020 rover Perseverance there, as the rover is carrying some technological demonstrators that will be useful in the development of technologies for the future astronauts that will go to Mars, and also other instruments that will help us understand deeper and have a deeper understanding of the Mars environment, which is important for future human missions on Mars. The rover, it's more complex than other rovers that are now on the surface of Mars, with the exception of Curiosity. It's much bigger. In this case, the size of the rover is driven and also has something to do with the source of energy that we are carrying. Instead of solar panels, this rover is taking radioisotopes electrical generator that allows us to have a bigger rover with more power, more power for electrical power for the instrumentation. I think we started working in this project in 2014. I remember well because I was on my honeymoon when I received the news that we were selected for the instrument we were participating in. SuperCam was selected for the final payload, and since then, until the delivery and launch of the mission, it has been a really exciting path that we have taken. We have taken in the University of Valladolid. The rover is quite big; it's almost the size of a regular car, as you can see. And the payload is quite interesting. The payload is designed to help to make the decisions of where to catch the samples, but also would allow us to have a direct detection of possible biomarkers on Mars if we are lucky. Starting with the remote science instruments, we have 2 panoramic cameras, Mastcam-C, that also carry several spectroscopical filters that will allow us to have some spectroscopical identification from the targets that we are imaging. We have SuperCam, which is the instrument in which we participate, that we will explain deeper later. We have MEDA. It's the great contribution from Spain and our colleagues from the Astrobiology Center in Madrid and INTA. MEDA is the weather station. It's a direct evolution of REMS, which is part of Curiosity, and it's telling us it's part of the 3 weather stations that the Astrobiology Center in Madrid has right now on Mars working. This is another instrument important for human exploration, as winds, dust storms, dust devils are important if we want to put humans safely on Mars. We also have contact science as SERLOC, which is one of the two Raman spectrometers along with SuperCam. In this case, this is an ultraviolet Raman spectrometer that is very focused on the detection of low concentration of organics. And we are complementing SERLOC in the arm of the rover with Pixel, which is an X-ray fluorescence instrument that will tell us the elemental composition of the targets that are analyzed by the arm. We have also a radar, a subsurface radar, RIMFAX, that will tell us if we have water or up to what depth under the surface of Mars. And MOXIE is that technological demonstrator that I was talking about. MOXIE, it's actually doing it. It's producing oxygen from the carbon dioxide of the surface of Mars. This is important because not only the astronauts need oxygen to breathe, oxygen is also used as fuel. So if we can produce liquid oxygen on Mars, that means that we don't need to send the oxygen for the trip back to Earth for our astronauts. We can produce that on Mars. And in that case, things that the impact of the dust or the perchlorates in the atmosphere of Mars, everything needs to be evaluated, and MOXIE is doing that. We are evaluating the performance of these instruments before we think about sending a full-scale MOXIE to Mars before the astronauts are sent, and check if we can produce significant amounts of oxygen from the CO2 on Mars. SuperCam, which is the instrument in which we participate, it's a very exciting instrument. It's a remote science instrument, but incorporating several analytical techniques that give us a unique idea of the targets we are analyzing. On one hand, we have leaves. SuperCam is directly derived from the instrument ChemCam on Curiosity, which perform leaves and imaging. In this case, we are doing leaves, as ChemCam did, or is doing, because ChemCam is still working since 2012, which it's going to give us the elemental composition of the targets on Mars. This is the building blocks of the minerals we have on Mars. We also have a Raman, in this case, a time-resolved Raman, that will operate also at without the need of contact. I'm now showing you the different distances at which we can perform each technique. If we want to obtain a Raman spectrum from a target that is far, up to 7 meters or several meters away, given that the effect is a very fine effect, as Fernando introduced before, we need to increase somehow the power we get from the target in terms of Raman scattering, and we need to focus on the interesting information we're getting, the interesting light we're getting from the target. For that, we are doing Raman in its time-resolved version. We use a pulse laser, which increases momentaneously the amount of Raman scattering we have. If we think about 14 millijoules, it's not very high energy, but when we think about this energy in a short pulse of just a few nanoseconds, we have really high power of the laser delivered to the sample. This is in the order of the megawatts. So that means that we also have a high power coming out of Raman scattering from the target we are analyzing. And we also need a specific detector to catch that information in that very short period of time when we have the Raman. So yeah, we have a time-resolved Raman, which is a very interesting evolution of the Raman spectrometers, the contact Raman spectrometers we were having. Raman will tell us the molecular and the structure of the targets. So if we think about the minerals and the rocks on Mars as Lego constructions, buildings, leaves will tell us the small pieces of Lego we are having there, and Raman will tell us how we attach those pieces one with the other, which is a full characterization of the target. It's a very interesting field of work in which we have been working. Is the combination not only for identification, also for quantification of Raman and leaves. We also will perform luminescence, which is a different technique. In this case, we look for the fluorescence induced by possible organics or minor elements, rare earth elements, as in some minerals that we could get from Mars. The instrument also incorporates the visible and infrared reflectance spectroscopy, which is another vibrational spectroscopy similar to Raman that will give us also some idea of the mineralogy on the region. In this case, since it's a passive technique, we are not limited by the energy we have to deliver of the laser to the target, so we can perform VSIR analysis of very distant targets up to several kilometers. And we are also recording the audio. We are recording the sounds from Mars for two reasons. First, we get the sound of the laser shots on the targets when we are doing leaves. Leaves is vaporizing, using the laser pulse to vaporize a small amount of the target to analyze to take that elemental composition of the target. So the sound the target does when it's hit by the laser give us some idea of the texture of that target, how hard it is. It's just a lot of sand, very conglomerated. It's a whole rock. That kind of information can be extracted from the audio we record. But also audio recorded by SuperCam allow us to know better, know more things about the atmosphere and the environment on Mars, like the wind gust we get, the possible dust devils, which are small, how you say, small tornadoes, let's say, on the surface of Mars. That can be investigated by our microphone on SuperCam. And it's also used for rover diagnosis, as we can get sounds from the rover when it moves different parts. And so it's a very useful tool. And the whole instrument, SuperCam, give us a lot of options to research on Mars. We do atmospheric, we do mineralogy, we help the rover with the diagnosis. And we also have this camera, the imaging capability, which is, by the way, the highest magnification camera on board the Perseverance rover, which is used to analyze distant details of the surface of Mars. In this case, we are using these days this information to analyze possible places where we are going to with the rover and check the morphology of those places before thinking about going to the rover in the months, in the following months. SuperCam is a joint effort of several countries in this case, but with three main members of the team, with Spain in front of the calibration target. That's what we did. France on charge of the MASH unit, where we have the telescope, the VSIR spectrometer, and the laser. This is done by IRAP on Toulouse. And then we have the body unit, where all the spectrometers are included, which is developed by Los Alamos National Laboratory, which are also the leading institution in the instrument. And we have also collaborations from different institutions in Denmark, in Canada, and different universities in Spain as well. So it's, again, remarking the importance of the team, and this is a team effort and an international effort in which we are eager to collaborate with our friends from India. This is our collaboration with the mission. I did the project management and participated along with Guillermo and Fernando in the development, design, and also the assembly of this piece of hardware. This is the calibration target for SuperCam. As I introduced before, we have several techniques that need to be calibrated individually. Each technique may have has its own needs in terms of calibration. So we have several targets to calibrate the imaging capabilities of the instrument, along with this RGB and the white and the dark targets that also are used to calibrate the VSIR spectrometer. We have several targets, mineral targets, that are used to calibrate the quantification capabilities of our LIFS instrument. And we also have these two targets here that are focused for Raman. We have a diamond that will help us to understand how our laser is behaving, and it's giving us information of the excitation source we're using for the Raman analysis. And we also have this organic target here. This is a piece of PET, a polymer similar to the calibration target from RLS on Exomars. What we are we are using this target to monitor how organics are aging on the surface of Mars. And for that, we are using the Raman Spectroscopy with SuperCam to check how this how the environment of Mars is introducing changes in the structure and molecular composition of this organic target here. Some of these targets are sensitive to the dust, so for that reason, we included a magnetic dust protection system that was also implemented during for Curiosity mission, for Curiosity rover in the mass-cam calibration target. As we know, a great part of the dust on Mars is ferrimagnetic. This means that it can be attracted by a magnet. So we use these magnets to drive the dust to selected zones and keep the central area of these sensitive targets as clean as possible during the time of the mission. The mission is since February this year in the ISRO crater, which is this small crater here in the between the Syrtis Major and the Isidis impact basin. It's a very interesting zone because we know that at least in two moments in the past of Mars, there was liquid water in ISRO, and the water in ISRO remained there until the very last stages of the climate change on Mars. We can also identify common structures that we identify on Earth as this deposition delta and inlet valley of water coming into the lake, into ISRO, and this outlet channel where the water left the lake. Here in a deeper detail. This is where the rover landed in February, and the aim is to keep exploring this area here and then move out of the crater as we analyze the very rich mineralogy in the delta of the deposition delta in ISRO crater, which the zone where we are right now, it's filled with olivines and according to the data from orbiters, and we detected some evidences of igneous rocks. This means that we have some volcanic and interesting activity here in this region, but then we are moving to the delta where we have another kind of mineralogy is more interesting from the point of view of the astrobiology, where we hope to, because smetites, carbonates means interaction with water, and we expect that these minerals could preserve the biomarkers that from possible life forms that could happen on Mars. The rover, you have the videos. I didn't want to put the videos here because it's quite long, but if you haven't watched the videos from the mission and how the rover lands on Mars, I recommend you to do so because the video is very impressive. The rover is suspended from a sky crane, is the name, and then it gets to the surface of the planet just using 3 cables, and it's descended by this landing stage. And then the crane, when the rover is safely deposited on the surface of Mars, the crane just moves away and crashes very far away from the rover. It's very impressive, and for the very first time, this is not the first time they use this system. It was developed for Curiosity, but it's the very first time we had dedicated cameras to record the process, and it's very impressive to watch. I recommend you to watch these videos in the page, in the website of the mission. For us, the very expected moment was the moment we got the very first images of our system on Mars. Here are the very first pictures we got 2 sols after the landing of the rover of our calibration target. You can see here now how some dust from the landing, where the rockets are moving a lot of dust and soil from Mars, are trapped by our magnetic systems and were moved away from the center part of the targets that are more or less clean. It was several sols later when this happened, and this is the very first Raman spectrum taken out of the Earth. And in this case, it was taken from the diamond of our calibration target. Very exciting moment. This means that the instrument was working fine, that we could do Raman, and in fact, we have been using Raman since then. But as you can see, it was challenging to get this spectrum. Very interesting. Again, this is a landmark for everybody in the Raman community and for space exploration, because this means that Raman is there, Raman is on Mars, Raman is working on Mars, and Raman should be and will for sure use in future exploration missions in the solar system. I just wanted to add some pictures and notes on the very first targets we analyzed. Papers, tons of papers will come in the following months as soon as we are clear to make to publish the results. But the very first targets we analyzed, we could see the first we saw were these structures here, these rocks with these bentifacts that give us the idea of these rocks being from a volcanic origin, which is interesting because that means we have energy in that place. We had geological energy. We could have processes that could heat water. We could have hydrothermalism processes in the region. This is the very first target analyzed by SuperCam. The first target is called MAS, which means Mars in Navajo language. And we just analyzed them with LIBS, and we discovered that this was a calcium-rich igneous rock going in the direction of having igneous activity in this zone. But most interesting is that we discovered that the hydrogen presence of this target means that it has a igneous origin, but it could be alterated by water, and also some hydration can be present on the target. This means that this is very important from the astrobiological point of view, because these alteration processes are important for life, as they transform the minerals and the chemistry we have there into very interesting chemistry for life and how life works. The process and the work is a continuous process, and I may have to update this. The rover will continue its path to get out of Jezero crater in the following months, but we are first aiming to analyze these regions over here and then move to the delta, where we are getting to those very interesting mineral deposits. And we are hoping to perform in the following months the very first sample catching from interesting targets on Mars. I can tell now that the option of going through this path has been the scope. We are going directly to the delta, and once we are out of the crater rim, we can think about an extended mission exploring other areas. But the idea is to have a very good understanding of what happened in this delta and check if we had life on this lake on Mars. And this is the end of my talk. As JPL, the Jet Propulsion Laboratory that assembled the rover, has used as motto, "They're mighty things." I think that's something we should do as scientists, and for sure when we think about their mighty things on other planetary bodies, send more Raman spectrometers is one of those mighty things we need to do. Thank you very much, and if you have any questions, we can talk about that now.
Thank you so much for this very detailed description and explanation. The amount of cutting-edge information you have shared is truly amazing. And we now open the floor to questions from the panelists and from also the assistants. Before we do so, I have as a layperson, I have a kind of a simple question. When you say you've taken the first sample out of Earth, do you mean the soil on Mars? do you, as scientists, call the same, Earth in Spanish is tierra, and we say, when we say we land on Earth, we say, and aterrizar. So, do you still call it Earth, or isn't it better to say soil?
Sorry.
Martian soil, yeah. So it's a bit confusing. I think though Earth in English it means both things, planet as well as soil. It's probably easier to call it the Martian soil. To avoid.
I use it incorrectly mostly. Yeah. I meant.
So that was the first sample taken out of the soil on Mars, which was when? Which date?
No, it wasn't taken. It's the first target we analyzed.
The first target analyzed. Of course, it's not. It's not brought to Earth yet.
No. If the rover hasn't even started getting samples into the tubes I introduced. So that's something. It's still pending. We have just I don't remember. We have 20-something tubes, I think. No, maybe less. We need to take the decision really carefully of what samples are we taking back to Earth, because we have very limited slots, and we all want to hit the jackpot of detecting biomarkers. So that will be a complex decision and still has to be made.
Okay, thank you and good luck. So Professor Umesh Khadane, he's lifting his hand, and I request other panelists and assistants if they would like to raise their hands, and our technological assistant here, audiovisual expert, Alvaro, will allow speakers and panelists to pose their questions from now. Yes, please, Professor Khadane.
It's really definitely very interesting, the ideas and the implementation, and can imagine how much work has gone in. One of the things which helps in a university environment when such work is done in a university is the students benefit from it. So how do you involve your students in these activities? I mean, only at the PhD level, or even master students get a chance to at least do maybe the science work associated with it, or maybe some design work. So how do you involve them in these activities?
If I can start, just as an example, we are presenting today. One of my students is presenting today his capstone of the degree, which has been helping us in the calibration and characterization of our emulation hardware of SuperCam here in our laboratory that will help us performing support science to Mars 2020 mission. And so, we involve students at all levels. Of course, given the time frame in which you have master students or degree students, you cannot, or you're limited in the kind of data you can share with them, because you have them for a very short period of time. With PhD students, it's a different thing. They are here for years, so they have the time to get into the mission, have the data, let the time, I don't know how to say it in English, the time that in which the data is, I don't want to say secret, but it's kept inside the mission. So they have more time to use the data of the mission. That's not the case with the degree and master's students, but we take them and we do interesting works with them in the related with the missions also.
Thank you. There's another question from Shyama Narendranath, URSC, ISRO, addressed to Professor Fernando Rull. What are the key improvements in the design of planetary Raman spectrometers over the years? And second part of the question, what could be the design elements that have scope for improvement in the future?
One of the key element of the key unit in the Raman instrument is the laser. The illuminating system is extremely difficult, not only for development, but also for qualification. because when you develop for the space application or for Mars application, you need to qualify. And qualify means to support extreme variation in temperature, also pressure, shock, vibration, and so on. And this is extremely difficult for LESA. Then LESA is a key element. Also, the grating is the grating, even if in the case like the Raman for Exomars or even the Raman for SuperCam are grating with no moving part, that means are solid in the framework of the spectrometer, also are key element, critical. And in general, all the optical component, also the optical fibers, the detector also suffer a lot with the radiation, with the different temperature and so on. And I think that for the future that we need for the Raman spectrometer is to increase the luminosity, that means the capture of photon, because as we comment in the talk, Raman effect is a very, very weak effect. Then we collect in general 1 photon for each 100 million of photon incoming from the laser. Then we need to improve this collection. Okay, maybe other in the future other possibilities are related with also improvement in the gate system. When we are using pulse laser, the gating system is also a difficulty, an extra difficulty, because we need to capture the photon when it's just coming from the sample. And this is, we know the light speed, and this is quite difficult. For the next future, I think that is the most important aspect that we have to consider.
Thank you, Professor Rull. I think we're running out of time here, but we can still take 2 more questions, perhaps 2 or 3. There's one addressed to Dr. Guillermo from Shama Narendranath. Could you please tell us more about the complexities in modeling Raman spectra to derive quantitative mineralogy? It's a complex question, perhaps, but if you can sum up and perhaps later reply in writing also, but if you want to address this question.
Yeah, sure. So actually, we don't do a lot of modeling. What we do is interpreting the data we get. So we don't do theoretical modeling of the theoretical emissions, but we do post-processing analysis on the data we get. So we deconvolve the signals to get information. We have on these processes that we use, we have used several techniques. Some of them are quite simple. We just look at the intensity of the different peaks along the different points that we have analyzed, and then compare them by simply doing the average at each point, and then we average all of them, and this gives an idea of how much of one element or the other you have. But also we are using or implementing machine learning techniques such as artificial neural networks or PCA, PLS, all these kind of techniques that take a lot of a bunch of variables and then work with them like in a black box to do the quantification. So it depends actually on the application that you want to do.
Thank you. There's another question here, which is related to Raman signal. The question is, as Raman signal is weak, how much signal enhancement was found in the case of time-resolved Raman in comparison to CV Raman? If any of you would like to respond to that, or if you want to take your time and respond in writing later.
It's can answer of Fernando. It's difficult to quantify the improvement. We can just say it's a binary thing. I cannot perform Raman at a distance of meters unless I have a very powerful continuous laser. and that can harm the sample and introduce alterations. I remember Fernando at the very beginning, we were performing standoff Raman with a continuous laser, an argon laser, but that was a very powerful laser, and we used the selected targets that were very good Raman scatterers. So the thing is of time resolved Raman is not only that we produce more Raman scattering by the use of a powerful pulse laser, is that we also take the characteristic of the laser that is emitting laser in a very short period of time to use a detector that is giving us that time resolving power that is acquiring information in a very short period of time. And we combine both advantages, so we can focus exactly on the period of time when we have Raman scattering of the laser. So if we are not competing with, for example, sunlight, otherwise we are on the surface of Mars, we are operating during the daylight. Otherwise, we will have all the light coming from the surface of Mars because we are using a green laser. So Raman scattering is happening on the visible range. So we need to get rid of that, and that's the way in which we can improve the signal of the target when compared to the other signals coming from the surface of Mars. So it's hard to say, quantify the improvement. It's more a binary thing. If we don't use the time resolve, probably we cannot perform Raman spectroscopy at that distances.
Mm-hmm. You know, if I may, on the other hand, the fact that we are analyzing samples at several meters distance makes that the solid angle of light that we are getting is much smaller than when we use continuous wave on a very short range. So usually what we gain by doing the time resolved Raman, we might be losing because we don't get as much light as we get on a closed system like the CD Raman or the RLS instrument.
Yeah, and in addition, final comment, we can't increase the power with the pulse laser because we arrive to damage the sample. And then Raman spectroscopy is a totally non-destructive technique. Then we can damage the sample because we induce transformation on the material that we are observing. And this is not possible.
Yeah, thank you so much. There seems to be quite a bit of interest on some of the related issues. We really crossed the time limit. I think Professor Umesh Kadane has a comment to make. Yes?
It's not about the technical discussion. Actually, our ISRO team from Space Science Office, they have some network issue. So they logged out in between and they were unable to connect back to the team, to the meeting. So they have just conveyed their apologies. They were trying to communicate again, but it didn't work. So I just thought I'll inform the team before.
Yeah. Okay. I have. I'm going to read the other three remaining questions, and if the Spanish team feels one of them, choose one of them. I'm not able to judge which one is more interesting, and the others, I please request you to reply in writing. If you can give us your email address. There are three questions here. One is about the surface. Which says the Martian surface is not so flat. Is not flat. So, is there any correction needed? That's question number one from Deepak. If you want to send your email ID through the chat, so if they may want to reply, if there's not enough time now. The second question is how effectively Raman measurement can overcome the issues of high proportion of transition metals like CR on the surface of Mars. And the other question there is related to a query from Anil Shukla from PRL Ahmedabad. As I understand, the laser 785 nm or more may be better for identifying organics or life, but on Perseverance or even on ExoMars, the selected wavelength is more suitable for inorganic. Are we not compromising the question for finding life on Mars? So these are the three questions. I request you to reply to one of them, and the other two questions that remain unanswered, if I I will request the persons who have posed the questions to send their email ID so that they may get a response in writing. Please, Fernando.
Okay, only, okay, I agree. We can reply writing by email the other response. Only for the question related with the excitation wavelength. I spent a lot of time analyzing the different possibilities. And the question, the main problem and main question related with the 785 nanometer excitation is that many bands, including organics, are in the infrared region, in which it is quite difficult to detect by technical reason, but also by fundamental physical reason. There is a law, the full power law, and in the high wavelength region, the intensity is following the inverse of the full power law of the wavelength, and the intensity decrease enormously. Then it is extremely difficult to detect OH-CH band with this excitation, except if we transform the detector in the infrared. Then for the visible observation, it's better to stay in the 532 nanometer excitation.
Thank you very much. It's really a pleasure, and there's so much to be learned, and we are all sharing this amazing team that you know, the university has put together. We're all sharing information on something which I believe has interest both for the layperson and the scientist. I think the presentations have been very well and suited for students as well as scientists. So I congratulate the team for that. But I now pass the floor to Mr. Chittireddy Sripal for the vote of thanks on behalf of Embassy of India in Madrid. On my behalf and Casa de la India team, we are very proud to have been able to host this session, and thank once more ISRO, IIST, Embassy of India, Ambassador Verma, and Professor Fernando Rull, his team, and Paloma Castro, Pro-Vice Chancellor. Please, Sripal, if you may proceed with the final remarks.
Yeah, thank you, Senor Guillermo, for this, for passing on the mic to me. Firstly, let me thank everyone from Professor Fernando Rull's team. It has been a magnificent webinar which showcased their work, and the other participants, including Dr. Hassan, Dr. T.P. Das, Professor Umesh Kadane from IIST, as well as Vice Chair Chancellor of Valladolid University, Paloma Castro. And let me also thank especially the Ambassador of India to Spain, His Excellency Mr. Sanjay Verma, for his interest in this webinar from right from the beginning, and for pushing this webinar. I would like to thank Professor Rull for his magnificent explanation of the non-intrusive nature of Raman spectroscopy, as well as the explaining to us the genius of Dr. C.V. Raman in separating the Raman radiation from the other radiations, which must have been quite a task in those days. And I would also like to thank Professor Rull for bringing in one of the finest scientific minds of India, Dr. Kalam, through his message that he has given in 2005 to Indian citizens. So it is remarkable that he has brought in one of our greatest scientific minds into this webinar. And finally, I would also like to remember K.S. Krishnan, the student of Dr. Raman, who was key in the discovery of Raman effect. And we at Embassy of India, as well as Casa de la India and other stakeholders, are also looking forward to the reciprocal webinar by the Indian institution in September. And I hope this webinar is a small step, but a giant leap forward in bringing or taking our relationship to the next level. Thank you.
Thank you so much. And with these words, we conclude the session, and I'm sure it's not going to be the last interaction with our Indian partners. We will surely plan in September, with the start of the academic year in Spain, a session where we will listen to the scientific application of certain Raman spectroscopy research from the Indian side, our Indian partners, or any related subject that they may choose. We look very much forward to allowing our students to know more about your work in India, and of course for scientists to work and collaborate together on actual research projects. Thank you so much. We greet the audience also that is listening to us from all over India, Spain, and anywhere in the world through YouTube and social media. And warm hola, namaste to you. Thank you so much, and have a good day on Earth and on Mars. Goodbye.
Bye-bye. Thank you very much.
Thank you very much. Thank you from IIST.
Bye. Bye-bye.